We are trying to figure out here if there is a camera at this elevation of this function, thinking about a similar to a roller coaster. On the x-axis, we have the time in seconds, and the y-axis is the height in feet. What we're trying to do is try to take a picture at this elevation here, but we don't know that elevation, and we don't know the speed of the cart. So we're trying to do this, and by doing that, we're going to try to find slopes to approximate the speed at that location. What we do know at the moment is this elevation here, this here, and more specifically when t is 5, 10, and 11 seconds. That each elevation is 0 feet. Because I'm the designer, I know that the elevation at 2 feet is 432 feet, and I should say at 2 seconds, not 2 feet. The best way, or not the best, but currently the best way of finding how fast this cart is traveling, in order for me to know exactly when to take a picture here, is to finding a slope of how fast this cart is moving. At the moment, we only know this elevation, as well as their time. So the best thing to do is to approximate this slope right here. If you remember slope from Algebra 1, it is a rate of change. In order to find that slope of that black line that was just created, all right, we are going to use 0 minus 432 over 5 minus 2, which is negative 432 over 3, which comes out to be negative 144 feet per second. So the slope of that line is negative 144. So that means that this roller coaster, is traveling about negative 144 feet per second velocity-wise. So that's a good approximation to figure out this speed or this velocity in there. A better way to know this at this location is to find an interval much closer to this here. So if I know this elevation here, then I can find the slope of this blue tangent line. To find the elevation of that blue secant line, I need to find the elevation at 3 seconds. If that elevation is 336 feet, again, I can find the slope of that blue line or blue segment, and that's going to be 0 minus 336 over 5 minus 3. So negative 336 over 2, and that actually is negative 168 feet per second. That gives us a better approximation of how fast this cart is going anywhere on this blue line. Now I want to get it closer to this here, so that means I have to get a closer approximation, a closer slope. So if I knew this elevation here, that new purple line between 4 seconds and 5 seconds, that's going to give me yet a better approximation of the slope or better yet, the velocity when we have here, let's say this is 4.4 seconds. So if the elevation of the roller coaster when at 4 seconds, if that is 168 feet above the ground, then again, we can use the slope formula. 0 minus 168 over 5 minus 4. That's negative 168 over 1, which comes out to be negative 168 feet per second. So this means that the cart from 3 to 5 seconds is moving at the same speed from 4 to 5 seconds. So this is going to take us into here before we move on to the vocabulary. In your calculators, I want you to use your 84s, your graphing calculators, whatever you have, to find these 6 values when this is the function. F of x equals negative x to the 4th power plus 26x cubed minus 215x squared plus 550x. Find those 6 values, and then we'll get started with my unofficial definition of those vocabulary terms. So in the calculator, you should have gotten 360 feet for 1 second, negative 120 feet for 6 seconds, negative 168 for 7 seconds, negative 144 for 8 seconds, negative 72 for 9 seconds, and negative 168 feet when the time is 12 seconds. So far here, what we've done is figure out slope of 3 secant lines. Those 3 right there, right? The reason we're doing that is because we want to find a very close slope when the time is 4.4 seconds. Right, we've been analyzing 3 different lines getting closer and closer when time is 4.4 seconds. Right, we've been changing things up. So in this case, that brings up to the first definition, right, of our vocabulary. Calculus. My definition of calculus is the study of things that change. In this case, with the roller coaster, what's changing is the speed between these 3 points and ending here at 5 seconds. We've been taking 3 different intervals of time. So my definition for that is a duration of a time segment. So we had 3 different segments for the blue, for the black, and for the purple lines. Right, those time segments or intervals of time was 3 total seconds for the black one, between 2 and 5, 2 seconds for the blue line between 3 and 5, and 1 second for the purple line between 4 and 5 seconds. These 3 segments, the black, the blue, and the purple, are pretty much also called secant lines. Those are straight lines or straight segments joining 2 points of a function. So if we look at those blue, black, and purple line segments, all right, here's the black, here's the blue, and this is a purple one I'm referring about, those are secant lines because they connect these 2 points, these 2 for blue, and these 2 for purple of this function right here. So we did find slope because the slope is not constant. It's not the same between those 3 units of time or those 3 intervals. This is our new definition, or our definition for average rate of change. It is a measure of how much a function changed over a certain time. Average rate of change, a measure of how much a function changed over a certain amount of time. So we have 3 different intervals of change, time intervals: 2 to 5, 3 to 5, and 4 to 5. That is the average rate of change. When we found this slope of the secant line, right, that is also the average rate of change that we found. So those 2 are very, very intertwined, very mixed together, because they mean the same thing. If you found the slope of the secant line, that is also the average rate of change, or your average slope between those 2 points. Let's use the first interval. As you can tell, right, if from here to here, right, there is no straight line, in order to find that average rate of change, we need to find the slope of that secant line. And because we're taking averages, average of this slope, this slope, this slope, this slope, all these until I get to here, that is going to be my average rate of change, which was negative 144 feet per second. Now, a tangent line is a straight line that touches 1 point on a function. Again, a tangent line is a straight line that touches 1 point on a function. So, for example, if I'm trying to find a tangent line here, there are going to be multiple tangent lines, but only one exists when time is 1 second, which is right here. When time is 2 seconds, this is approximately that tangent line. This is approximately tangent line when t is 3 seconds. When t is 4 seconds, t is 5 seconds. When t is 6 seconds, this is about the tangent line. 7 seconds. Here's about 8 seconds. At 9 seconds. And 10 seconds. Those were there are tangent line because it only touches the function 1 time at that 1 point situation. Now, instantaneous rate of change is a measure of how fast an object is traveling at one specific point. A tangent line is a measure of how fast an object is traveling at one specific point. So in this case, I want to know the instantaneous rate of change when t is 4 seconds. That way, I can set up my camera somewhere very close to the roller coaster. That way, I can catch the facial expression of the riders. So the theme park will cash on selling these pictures. This is also, by this, I mean the instantaneous rate of change is also the slope of a tangent line. If I know the slope of that tangent line, I also know the instantaneous rate of change, which is also known as IROC. So if I am trying to find the instantaneous rate of change when t is 4.4 seconds, I want to know this tangent line right here. That way I can find this slope. And if I can find this slope, I know the instantaneous rate of change at 4.4 seconds. And the best way to do that is to theoretically speaking, get as close as I can to this 4.4 seconds, which pretty much means that I need to be equidistant away from the 4.4 second. So in this case, I can do 4.3 and 4.5, so I can find the instantaneous rate of change there. So what I'm going to do, all right, to find the instantaneous rate of change at about 4.4 seconds, what I need to do is I need to figure out, just like we did in the table, if I have x and f of x, I need to be on one side of, or I should say the left side of 4.4 seconds, and the same distance on the right side of 4.4 seconds. So in this case, I don't care what this part is here. All I care is one to the left and one to the right of 4.4 seconds, as close as you can. So 4.3 and 4.5 seconds. So now I am going to use this function to find these two values. And those two values are 114.9519 and 80.4375. So that means that I need to find the slope of, or between these 2 points, I can get a better instantaneous rate of change at 4.4 seconds. So the slope equals, this is going to be my second point. This is going to be my first point. So this is my x2, x1, y2, and y1 for my slope formula. 80.4375 minus 114.9519 all over 4.5 minus 4.3. This math will simplify into negative 172.572 feet per second. So the instantaneous rate of change at 4.4 seconds is about negative 172.572 seconds. I'm sorry, negative 172.572 feet per second. I mentioned that my unofficial definition of calculus is the study of things that change. If I want to change this interval, the 4.3 to 4.5, and get closer to the 4.4 seconds, yes, I can do that. Instead of using tenth or 0.1 from each side, I can go at a smaller number and use 0.001 of a difference. The closer and closer you get to 4.4 seconds, the better of an approximation for an IROC, or instantaneous rate of change, you will get for at that location here. Because we are changing that interval, that brings up to the last definition of limit, or unofficial definition of limit, which is a value that puts a function, it is a value that a function approaches. So a limit is a value that a function approaches. So if I want to get closer and closer, finding the limit as x approaches 4.4, I know that I need to be very, very close to 4.4. So if I am on the left side, that would be 4.39. If I still want to get closer, I can find a number that's between 4.39 and 4.4, which is 4.399. And there's still yet a number closer or in between 4.399 to 4.4, which is 4.3999, and so on and so on. This type of mentality is limit as approaching 4.4, and we'll get to those starting tomorrow.